The fish passage is designed to replace a traditional dam but still reduce flow while letting fish swim through it. It needed to be at least 5 centimeters high, 20 centimeters long, 7.6 centimeters wide, and have a continuous 1.3 centimeter opening to allow the fish to swim through. The 3D printed structure would be placed into riverbeds where it is needed, so we wanted our fish passage to heavily mimic the natural environment. We immediately thought of rocks and trees as great natural objects that we should incorporate to do this. This would allow for it to be minimally invasive for the environment and make it easier for fish to swim. To start the project, we needed some background knowledge on basic fluid mechanics and the general types of already existing fish passages. There was an excellent article from Colorado State University that showed many possible solutions. A diagram from the article is shown in the top right of this slide. It was helpful to see how different angles, spacing, sizing, and a different placement could drastically affect the flow of the water through the passage. We did not want the flow to be too chaotic and swirling, as this would affect the fish's ability to swim. We took heavy notes and inspiration from these sketches to create our brainstorming ideas in the next slide.
For the brainstorming section of the design cycle, we decided to do individual create individual ideas based on our collective research. So we all went and came up with 3 ideas, and then we came together and talked as a group. And out of those 15 ideas, we decided on a final 3. We wanted these final 3 ideas to be pretty different from one another so that if one ended up not working out, our backups wouldn't be essentially the same idea and we'd be able to take it in a different direction. So on the top left, the main goal is that's like a pretty easy way for the fish to flow through, and it's really just about directing the water more towards the center, then back out towards the side, and then back into the center again. On the bottom left, we sort of did a staggered conformation. This is really just about breaking up the flow of the water. We decided to sort of angle the pillars to make the water more easily flow over it. And then on the right, our third design, we essentially sort of created a second channel within the river to really just redirect the water to one side and then back into the middle.
So as we went through our first testing, you can see here on the picture, our FEDD project, the re-engineered fish passage, is in the flume. And what you can see is that the water is flowing through, and as it's going down, it's kind of trickling down. The height is changing as it goes through the system. What we ended up finding was that in our inflow measurement of the water that was going in, it was approximately 74 millimeters. And so that was the height of the water as it had been going through the system. So we got that measurement from turning on the flume, having the water go through, and then after approximately 3 minutes or so, the water had leveled out to a pace where you could see that the measurement will be accurate to the functionality of the engineering fish passage. And so, yeah, so we got 74 millimeters on that. We were quite pleased with that. And we actually, the gurus for the FEDD project were also quite impressed with it, which was really nice to see. We also had our outflow measurement, which was approximately 40 millimeters. And what we can see here is that that is the water, the height of the water going out. That is actually approximately the same measurement as what we got on the second iteration from the outflow, which is great. During the testing, we had found that the front row of the tree trunks that stuck up were slightly too high, which was why we saw that the water level had risen, such that there was backup because there was too much force going in, and it was getting possibly deflected by the height of the tree trunks there, as well as the large thickness of the trunks themselves. So one of the things that we noted down during our first testing was that the height of the tree trunks was too high. And so what we ended up doing was we ended up staggering the height such that it started down lower, and then as it went up, it went a little higher. And that would decrease the difference between the top water going in and the water coming out.
For the redesign, we sought to make 2 major design changes to the original design. The first was to make the trees thinner. Doing this increased the available cross-sectional area, which allowed for the flow velocities to be minimized. Initially, we did not know how much force the trees would experience when in the flume. However, the trees had no problem handling the forces in the first test, so we opted to make them 25% thinner. The second change was making the top of the trees have an upward slope. During the first test, we noticed how the water depth decreased for each row of trees. We saw how there was a drop of 10 millimeters, then a drop of 6 millimeters, then a drop of 3 millimeters. We believe that the additional height of the water above each tree would stay about the same if we made the first row shorter. As a result, the height of the water would be more similar to the downstream height. We also shortened the middle row of trees for the same reason. An additional extra change that we made was making the base a little bit thinner. This allowed for even more cross-sectional area and even less flow depth drop. During the next test, which was the final test that we would be judged on, we were extremely happy with the results of these changes. We were able to reduce the upstream depth by 20 millimeters and only had a 13 millimeter difference between the upstream and downstream flow depth.
So there were 3 main challenges we faced, the first being requirements. In particular, we had to come up with the designs that had the 1.5 inch. Actually, I don't know if that's right. Reset. All right, go in this time. There were 3 main challenges we faced, the first being requirements. We had to come up with designs that had the required opening throughout all of our designs, and that kind of hindered what kind of ideas we could come up with. Functionality, we had to come up with the designs that actually stabilized the water levels and outcompeted our opponents. So we couldn't just come up with something that might be visually appealing, but it had to really do its job. And the presentation to the judges at FEDD, we had to be very well articulated and describe everything that we had done in our project to the judges in person. Some shortcomings and advice. Our shortcomings were our bottom was too thin. We actually got saved and we found a way to put it in the flume where it wouldn't float away, but our bottom was too thin. And so that was a big problem for us. And actually our second print, the one we didn't even get to test, the bottom was so thin that it snapped in half. Some advice would be to bring multiple prototypes because you can test as many as you bring. So if you bring multiple prototypes, you can test several different iterations on your first time testing, and then you might know what you can expand upon and make your final for your second testing. And then prepare your presentation for the judges and be comfortable speaking and make sure that you all know your roles before you start talking to the judges.